Hello RubyConf, welcome to Parallel Testing with Ractors, putting CPUs to work. My name is Vinny, I'm a senior developer in the Ruby types team at Shopify. We work leveraging static typing to make our developers more productive. We've been doing a lot of work around Sorbet and Tapioca, and we are hiring. So if you're interested in joining our team, please reach out. And if you want to know a little bit more about my work, you can find me at Vinicius Stock on both Twitter and GitHub. In the last edition of RubyConf, we got the first Ractor demonstration by Koichi, and I really wanted to try Ractors out, in particular trying to run tests in parallel using them. Today I want to share a little bit about what I learned trying to do so. So we're going to take a look at a few test execution strategies to parallelize tests, an introduction to Ractors and how they communicate. We're going to build a mini-test-like framework, parallelize it using Ractors, and then we're going to take a look at a few highlights of the study, features and limitations of using Ractors. But what does it mean to run tests? So fundamentally, tests are just pieces of code that we want to organize and execute. It doesn't matter if in mini-tests they are test methods and in RSpec they are Ruby blocks. They're just blocks of code that we want to run in an organized manner. It then becomes a matter of how fast we can do it in order to reduce the feedback loop for our developers, and then we start getting into strategies for parallelizing the execution of tests. The first strategy we're going to take a look at is by using groups. So we begin by figuring out the tests that we want to run. We split them into different groups, and each group gets assigned to a different worker, to a different CPU, that's going to execute only its group in parallel. It's a simple strategy, but it doesn't guarantee even distribution of the workload. So, for example, if we end up in a situation, here CPU 1 got unlucky, it got randomized with a group that is larger, and it also has two integration tests which are slower than unit tests, then it's very likely that CPU 2 is going to be able to finish running its group faster than CPU 1, and in the end it's just going to sit there idle waiting for CPU 1 to finish when it could continue doing more work for us. Execution strategy number 2, by using a queue, tries to address this. So we begin just the same. We figure out the test that we want to run. We then organize them into a queue of all of the examples, so a list of all of the tests we need to run. And then the workers can pop items from this queue as soon as they're ready to do more work. In the case of mini-tests, it would look something like this. We would have a queue where each one of the items are test examples, which test methods, and then the workers can pop items from this queue as soon as they're ready to run more tests, avoiding being idle until the very end of the suite. The last strategy we're going to take a look at is called work stealing, and this is used in other areas of computing as well, but for our case here we're going to see that it's very, very similar to using groups. We begin just the same. We figure out the tests that we want to run, we randomize them into different groups, and we initially assign each one of the groups to a specific worker. The difference here is that if any of the workers become idle at any point, if they finish running their group before the others, they can signal that back to the main process, which is going to take work from one of the other workers and pass it along to the one that is idle. So if we go back to our original example for groups, we're going to begin just the same by having CPU 2 run much faster than CPU 1, but then as it becomes idle, it tells the main process, which is orchestrating all of the work, and then it reorganizes the work to guarantee that CPU 2 is not going to be sitting there and can actually continue doing work for us. Both strategy number 2, by using a queue, and work stealing try to guarantee even distribution of the workload. The main difference between the two is that work stealing it tries to reduce the communication overhead that we have from trying to speak to the shared queue. In the case of execution strategy number 2, every time a worker has to run a test, it needs to communicate with the shared queue to pop an item and start working on the next item of that list. Whereas in work stealing, each one of the workers begins with a predetermined list of tests and only needs to communicate if they become idle. So it reduces the communication overhead by quite a bit. But originally, Ruby did not have support for taking advantage of all of these different CPUs in our computers. So how do we currently parallelize test execution? For example, Rails ships with a mini-test plugin that can parallelize the tests for our applications, and there are many other plugins for all sorts of test frameworks that can do the same. In the case of Rails, it actually implements strategy number 2 by using a queue object that has all of the different test examples defined by our application. It then forks different Ruby processes, child processes, to build the worker pool that will run those tests in parallel for us. The last missing piece here is how do we communicate between the main process that holds the shared, the queue object, and all of the workers? How do we coordinate the work between all of them? And what Rails does is it uses a gem called DRB, which stands for Distributed Ruby, to do inter-process communication. So basically the abstraction that this gem provides for us is we can share a Ruby object between many different processes. And in this case, Rails will take the queue object and share it with all of the workers, so they just have access to that object like the main process and can just pop items from the queue as they do more work. But now in Ruby 3 we have Ractors. Can they perform any differently than processes? We're going to begin by taking a look at how they work. We can create a new Ractor with the method new, just like any other Ruby object, and the block that we pass to new is the code that's going to be run in parallel. So in this case, we're creating a worker that is receiving an item, so Ractors can send and receive messages, and in this case it's receiving an item, and it's going to do some processing on that item. As we reach this point in the code, the worker is actually stuck waiting to receive that item, and it's not going to do any processing until it receives something. So we can kick off processing by sending it some important information, and then we can use take to wait until that worker is done processing and take the return value of the block that we passed to new. A bit of a more involved example that we're actually going to be using in our test framework is a worker pool. So we begin by creating a queue of numbers from 0 to 99. This is going to be analogous to our queue of tests for the test framework. We create an array to store the results of our calculations, and then we build a worker pool of 10 Ractors, and each Ractor is going to be stuck in a loop, and for each iteration of this loop we're going to do two things. We're going to receive a number that's being sent to this worker, and we're going to yield that number back times 5 to the main Ractor. Here, yield is another form of communication available to Ractors that is typically used when we have to return values to the main Ractor at multiple points during the execution. So in this case, for every iteration, we want to return the number times 5. We know that all of the workers are going to be stuck waiting to receive something, so we can kick all of them off with an item from our queue, and then until our queue of numbers is empty, we can use Ractor select to find the first idle worker and the result that that idle worker has yielded back to us. We save that result in our array just to keep track of them, and we send the idle worker another item from the queue to keep processing. Notice that this loop ends when the queue is completely empty, when we finish popping items from the queue. But we can still have Ractors doing processing in the background, so we still need to go through each one of the workers, make sure they're done processing and take the return values, or else we're going to have incomplete results. Let's give Ractors a break and let's take a look at test frameworks so that we can actually build and parallelize one. I like to divide them into 3 areas of concern. We have execution, so how do we organize the work, build the queue, and dispatch that to the worker pool? Utilities and syntax, so what is available for us to test our applications? Is there assertions, expectations, stubs, mocks, anything we can use to test the application? And reporting is how do we display information to the user about what's going on and what happened during the test run. If we begin by taking a look at the example code here on the left, based on Minitest, we can try to extract some ideas of what we would need to implement a similar framework. So the first thing I want to call attention to is that the tests are just regular Ruby classes. So we can just require the test files just like we would require any other Ruby file. But we do have a special interest in those test classes. We need to be able to keep track of them because we're going to have to reference them later. And we know that each one of the test classes can define multiple examples, can define multiple test methods. So we need to be able to loop through each one of the test examples defined by each class and run all of the tests. If we zoom in into a particular test, we start getting into assertions and how do we define the syntax for testing our application. Assertions also need to be able to assist with the execution flow. So we know, for example, that in a test with multiple assertions, if one of them fails, then we already know the entire test has failed and we don't have to continue running. So we need to be able to halt execution and skip to the next test from our queue. We also need to be able to save information about what's going on, and particularly about failures, so that we can display that information at the end for the user. And finally, we can provide any sort of helpers that we like in utilities, such as stubs, mocks, anything that is a quality of life for our users. Finally, reporting is responsible for two things. We need to be able to display progress so that the user knows that the tests are running and what is going on. And at the end, we need to be able to display aggregate results and tell the user what happened, what failed, and why it failed. So let's actually get down to implementing it, and we'll begin by figuring out how we can keep track of all of the test classes that are defined. We know we're going to be requiring the test files, but how can we keep track of the classes that are defined by them? Well, one strategy we can take is by defining a class method inherited on a base class test, and we're going to define that every test must inherit from this class. And by defining this class method inherited, Ruby will invoke it for us every time our base class is inherited by another. So if we specify that all the tests must inherit from this base class, Ruby is going to call that callback for us, and we're going to be able to save all of the test classes into an array. This is already enough to get a list of classes that are tests, but how do we model our queue? Because we know that each one of those classes can actually define multiple examples, can have multiple tests inside of them. So we need something that looks kind of like this. We need to be able to have a list of tuples where each item of the tuple is composed of the test method that we have to run and the class that they belong to. We already have the list of classes, so let's try and remap it. And for each one of the classes, we're going to begin by listing the instance methods defined by it. And here false just ignores inherited methods. And then we're going to filter the instance methods based on whether they begin with the word test or not. Because we're only interested in test examples, but we know that we may have a setup method and a teardown and things like that that we're not interested for building the queue. If we have all of the list of tests that are defined, then we can remap it and return our tuples with the class and the test method, and we reach exactly the format that we were looking for. So this is enough for us to require the test files and get a list of classes and build our queue with each one of the individual examples. But now we need to be able to take one of the examples that we get from this queue and actually execute the test, actually perform the execution steps. In order to do so, we're going to begin by creating an instance of the test class that we receive from the queue. This is important for isolation between test examples. So we know that if we change the value of instance variables inside an example, it doesn't impact any of the other examples. And the reason is because each example runs in a completely different instance of the test class, which guarantees isolation for us, which is exactly what we want. And after we have the instance, we can take that instance and invoke all of our execution steps on it. So we can invoke setup, we can dynamically dispatch the test method that we got from the queue, and then we can invoke teardown to finalize the test, which is already enough for very basic execution. But of course, we don't have assertion, so we can actually test that our application works. Let's actually build the very fundamental assertion, asserting whether something is truthy or falsy. So in this case, if something is truthy, then we're passing the assertion. And in this case, if we pass, we don't want to do anything. We just want to continue running the tests. So other than maybe saving some statistics, we don't really have to do anything if our assertion has passed. If it fails, if something is falsy, then we do need to do some things. We need to be able to save information about that failure so that we can display it at the end for the user. And here, one possible way of doing so is by having a singleton instance of a reporter class that can aggregate all of the information about everything that happened during the test execution, and then have it all in one source to be able to display it at the end. After we save information about what has failed, we can then skip to the next item in the queue because we already know the entire test has failed. There's no point in continue executing it. We can just skip straight to the next item in the queue. It would look something like this in code. we would begin by incrementing the total number of assertions, so just some statistics. And if something is truthy, we can return early, which is when the assertion has passed. If the assertion does not pass, then we need to be able to register the failure. And here, whatever we register the failure with is what is going to be, is the information that's going to be available for us to display a summary at the end. So here we're using the current instance of the test class and a custom failure message. And then at the very end, we are raising a custom error class. The reason we are doing so, by defining a custom error class that we can raise when assertions fail, we can halt the execution of that particular test method and skip to the next one. Because we defined this custom error class, we can rescue it wherever we like, and so we can define the execution flow to rescue for that particular class and skip to the next item from our queue every time an assertion has failed. And every time an assertion fails, when we register that failure, we can also print some progress and display an F on the screen. If we go back to our execution steps, we can add some more statistics and reporting to it. Before we begin running our execution steps, we can increment the total number of tests, because we know we're running a single item from the queue, so we can increment the total number of tests that we ran. Then we begin our execution steps with setup, the test method, and teardown. And if we reach the very end of all of these steps, we can increment the total number of successful tests. The reason that we can do that is because we're raising that specific custom error class every time an assertion fails, and assertions would have failed inside the body of the test between setup and teardown, we can rescue that particular error class at a higher level than this execution flow, which then guarantees that reaching the last instruction it means the test has passed. And so we can increment the total number of successful tests and print a dot to the screen to display some more progress. We got all of the pieces that we need in order to make this framework work, but we need to be able to put everything together now. So we'll build an executable that's going to begin by requiring all of the test files. This is already enough to populate the list of classes. And then with the list of classes, we can go through our queue, through our list of tuples. And for each tuple, we're going to execute our execution steps that we define. So we're going to create a new instance and invoke all of those steps here represented by the method run. We know that as we run all of the tests defined in our queue of tuples, we're going to be populating the singleton instance of our reporter and reporting everything that happened to it. So at the very end, it should have all of the information in order to be able to print a summary and tell the user what happened during the test run. And our sequential test framework already works and can already run tests that are very simple and can only assert whether something's truthy or falsy. But let's actually parallelize it, which is our main objective. We'll begin just the same, and notice how this is very similar to our worker pool example, but we'll begin by requiring the test files to populate the list of classes. And then with the list of classes, we can take the queue of tuples and assign it to a variable. Here we're shuffling just to randomize the order of the tests. And then we're going to build a worker pool using the number of available processors, where the workers are going to be Ractors stuck in loops, receiving tuples from the queue that are being sent to them, and then running our execution steps for each one of those tuples. We know that they're all going to be stuck waiting to receive a test from our queue, so we can kick all of them off with an item from our queue, and then until we are finished running the entire suite, we can find the next idle worker and send it another test from our queue. And theoretically, this should already work. We are already running the tests in parallel, and it should behave as we expect. But if we try to run this, we're going to get an error saying that class variables are not available outside of the main Ractor. So we can't actually read or use in any way class variables from child Ractors, from Ractors that we spawn. And this is coming from the singleton instance of our reporters. When we build a singleton instance, we typically use class variables, and so that is what's causing this problem. We need to be able to aggregate information about our test run in another way that doesn't involve class variable usage. One possible way of doing this is by defining multiple reporters that only know about a particular test run and then create a mechanism in order to be able to concatenate them and aggregate the information in a single source. So we begin by creating a reporter in the main Ractor that's going to be the one that's going to aggregate all of the information. And then for every test that we run, we yield back a temporary reporter that can be concatenated into our aggregator. So basically we're getting information about each one of the test runs and then concatenating into a single source without using any class variables. And I just want to call attention that we do need to go through each one of the workers, make sure they're done processing and concatenate all of the reporters, or else we're going to have missing information at the end. And we managed to parallelize our framework. This is already enough to run tests in parallel. And this study is available at Vinicius.stock/loop if you want to take a look. I'll do a little bit of a demo and show how it works. Loop has both process and Ractor mode for parallelizing the execution of our tests out of the box. I have a test suite ready here, and I just want to display the differences between the two. We'll begin by using process mode first, and notice how it takes a little bit until we start getting output on the screen. The reason for that is because it takes a little bit in the beginning, it takes a little bit of time to fork all of the different Ruby processes and finally start running our tests. We don't pay the same price when we use Ractors, and so we'll see that we begin outputting to the screen much faster than in process mode. So for this very short test suite, it is actually faster to use Ractor mode. As I was playing around with Loop, I got overexcited and I actually built an interactive reporter that I just want to show very quickly. We'll introduce a few test failures here in our suite. And now we're going to run Loop, selecting the editor as VS Code. And by the end, because we have failures, we're going to get a paginated list of each one of these failures, pointing to the file and exactly what happened. So we can cycle through each one of these and click O to open it in the particular editor that we're using. Work on fixing the tests. If we click R, we can rerun only that particular example that we have selected. And if we're happy with what we got right now, then we can mark it as fixed and keep working until we finish fixing all the failures. So even though Loop is just a study, I still want to be able to extract the interactive reporter as a plugin for the other frameworks and hopefully provide some cool functionality for the Ruby community. Because Loop has both Ractor and process mode, we're able to measure the amount of time it takes to run a test suite as we increase the number of tests in both modes. And what I want to call attention to here is that for a low number of tests, Ractors outperform processes by quite a bit. The reason for that is because processes pay an initial cost for forking all of those different Ruby processes in the beginning to build a worker pool, which doesn't happen for Ractors. But as we increase the number of tests, this difference becomes less and less relevant because we're going to be spending most of our time in the application code and not actually in the test framework. So for a realistic test suite with a decent number of tests, it's likely that both modes will perform very similarly. A few highlights of our framework: it cannot make broad usage of class variables. So as we've seen in the case of the reporter, they're only accessible from the main Ractor, so we need to be careful about that. We also need to be careful about meta programming. So for example, if we invoke the find method from a Ractor, the method that is created only exists in that Ractor and not in any of the others. So we need to be careful about meta programming as well. And it can only test Ractor compatible code in Ractor mode. Because our application code is going to be tested, is going to be executed from within a worker, it's also going to be subject to all of the limitations that the workers are going to be subject to. So it's not enough for the test framework to be Ractor compatible. We also need to make sure that the application that's being tested is Ractor compatible, which may involve other gems and dependencies as well. It can run tests in parallel, so that's our initial objective that we managed to achieve. It can also test code that spawns even more Ractors, so if we're testing an application that creates even more Ractors, it does not matter, it works without any modifications thanks to the actor pattern. And finally, it doesn't pay the initial cost of forking processes, so perhaps for short-lived programs or for small test suites, it may actually outperform, Ractors may outperform processes. As we were putting loop under some stress, my colleague Peter Zhu and I managed to find a few bugs in Ruby. The first one we found is a segmentation fault when the garbage collector was sweeping right at the exact moment that we wanted to yield back a value from a Ractor. The second one is another segmentation fault when classes were trying to be freed from inside one of the Ractors. So for example, if we create anonymous classes with class new inside one of the Ractors, eventually it would need to be freed, and depending on the conditions, it would lead to another segmentation fault. And finally, we found a deadlock when auto-loading a constant for the very first time from within a Ractor. And I'm happy to say that we managed to fix the first bug, but we were not able to get to the other two yet. So Ractors still have some limitations, and we were able to see that we need to code in a specific way in order to be able to overcome those. But the reality is that they're still experimental and they will continue to evolve. Developer tools are a great opportunity to test Ractors and technologies like that, because we're not in such a high-risk environment as we are in our production servers. So it's easier for us to test it out, provide feedback, and help advance parallelism in Ruby. Thank you very much for listening to me. I hope you had fun during this talk as much as I had playing around with Ractors, and enjoy the rest of RubyConf.